Okay, so hello everyone. Let's officially start the first quantum machine learning workshop organized by Q Poland and Quantum AI Foundation, or Fundacja Quantum AI in Polish. My name is Paweł and I'm one of the organizers. And at the beginning, I will just give you a brief introduction and explain the design of this workshop and what you can expect. Let's start. So as you know, we'll have 2 days of classes, so today and tomorrow, starting at the same time, 10:30 Polish time. And the main instructor is Jacob Cebulski. So I see that Jacob is already with us, so he will soon take over the Zoom and start the merit part of the workshop. We have a few mentors. So some of the mentors are here on Zoom as well. All of them should be available on Discord. There was also one more person that helped us in organizing this event, Agnieszka Wolska. She helped us with preparing the graphics and banners, so we also would like to thank her for that. We've shared a link to the GitHub repository with all the materials for this workshop. It has been shared on the Discord. As you can see, for the lectures, we use Zoom. Discord is our backup option. There is a voice channel on Discord, but if there are no issues, we'll just use the Zoom link that we've already shared. The rest of the communication would be on the Discord. So if you have any questions, there are some dedicated channels on the Discord. There is the help category with some thematic channels. So if you have some specific questions, you can ask them in these channels from the help category. There are also some other useful channels with important links, with the rules, with code of conduct, and so on. But we believe that most of the discussions will be held in the channels from the help category. One important thing is that you can receive a certificate after this workshop, after solving the final tests. We'll share the details later. So we've already prepared the questions, but for the test. But as this is the first edition of this quantum machine learning workshop, we would like to wait until the end of the workshop to validate, to see, and to ensure that all the topics from the final tests are covered during the lectures. You'll later have about 1 week to complete the final test. And if you get if you receive sufficiently good score, then you can get a certificate. It's not mandatory, of course, but for those who would like to get some certificates, you will be welcome to do the test. So we'll announce the details later, probably tomorrow after the last session. Uh, all right. So as you can see, we use Zoom for the lectures, and we also have chat. So if you have some urgent on-the-fly questions, you can also try to post them on the chat of Zoom. As I said, some mentors are also available here on Zoom, and Jacob is here with us. Perhaps we'll be able to answer your questions on the chat as well. But by default, after the sessions, the Discord server is the default communication channel to ask and answer the questions. All right, so let me proceed, and later I will see if there are already some urgent questions. So I also wanted to tell you a few words about Q Poland, Fundacja Quantum AI, and QWORD. So these are the, let's say, organizations behind this workshop. So actually, QWORD is not directly involved, but Q Poland is one of the so-Q cousins of the QWORD. So QWORD is an international organization, so it's a global network of individual groups and communities collaborating internationally on education and implementation of quantum technologies and research activities. Yeah, see here you can see QWORD's link to QWORD's website, social media, Discord server. You can also join there and I will also later share the slides on our Discord, so you do not have to record these links now. And there are some interesting projects carried out in QWORK, like the workshops on quantum computing and programming, starting from the introductory level, like QBronze, to more intermediate level, like QSilver and QNickel. So basically, we work together globally to develop these educational materials. There are also some research programs, like the QIntern program that will start soon. So I believe that after this workshop, you should be able to apply for the internship positions within the QIntern program. So it's a program for of remote research internships in quantum technologies. The applications form will be publicly available within the next few weeks. And in QWORD, we have currently more than 30 Q cousins. So exactly, we have 36 formally. We have 36 Q cousins, and Q Poland is one of them. And actually, Q Poland was one of the 5 founding members of QWORD. And in Q Poland, which is one of the formal organizers of this workshop, we have researchers from different universities in Poland and quantum enthusiasts from the Polish quantum ecosystem. So you can also join our Discord group, mailing list, follow our social media, subscribe to our monthly newsletter, and so on. Yeah, so here are the links. I will later share them on the Discord as well. And finally, a few words about Fundacja Quantum AI. So in English, it's Quantum AI Foundation. It's a non-profit organization with the goal to support education, research, and collaboration in new technologies, especially AI and quantum computing. And we organize the workshops like this one and other events like meetups, contests, conferences, hackathons. We release newsletters and so on. All the events that we organize are free for participants. So this is one of the actions that we have. We believe that the access to knowledge should be free. But on the other hand, if you like our initiatives and would like to support us, you're also welcome to donate. Okay, and that's all from my side. If you have any questions now or after the session, you can also send me an email. I'm also available on the Discord. And let me just quickly check if there are some urgent questions on the chat regarding the organization of the workshop. I see that people are still coming, so maybe there are some new members. So it's interesting because now I can see only the last comment here on the chat. Okay, maybe someone would like to unmute and ask some urgent questions regarding the organization. Okay, I see some other comments. Okay, so there is a comment that the volume is low. I'm not sure if I can increase it. Is it better now? Okay, is it better now? Maybe you could also increase the volume on your side. Yeah, there is now a noise, but I think it's not from my side because I think that someone just unmutes, and this is the reason. So let me just, yeah, I think that the person is muted now. Is it better now? Could you please confirm that the voice is okay? Yes. Okay, good. It's better. All right, perfect. Let me go back to the questions on the chat. It has improved. All right.
Yeah, hello. I had a question.
Yes, please.
Yeah. So you said that you guys are like non-profit organizations, right?
Yes, yes,
So I might be wrong or I might not have much information. So I just wanted to ask you a question out of curiosity. So
yes,
going forward, like obviously some of the things have to be monetized, right? So
yes,
how are we like what do you think is the way to monetize or way to like put these technologies that we are getting out of our research into commercial uh in
yeah.
commercial aspects, right?
Okay, so it's quite a general question, not directly related to the workshop, but I will try to answer. So the thing that we are a non-profit organization doesn't mean that we do not have any incomes, because we also have some sponsors of our projects, our events, and we also receive some donations, of course. But of course, it's not a business entity, right? So we do not have business operations, and from the perspective of the participants of our workshops, everything is free indeed. We believe that the access to knowledge, the education should be free for people. So this is one of the general actions in Keyword. But when you develop some quantum technologies or other technologies, the way to go is to found a startup like a company, or you can also think about some other ways of monetizing. You can sell licenses and other things, but this is not something that we are going to do at least in the near future in the Quantum AI Foundation, right? Because we want to keep it a non-profit organization. So legally, a non-profit organization is not a good legal form to build a business entity, right? So if you want to build a business around your technologies, you should rather found a startup, a company. Like in Poland, we have something like spółka z ograniczoną odpowiedzialnością, which is a company with limited responsibility or liability, or there is something like a simple company as well, dedicated to startups, right? So there are some other legal forms of organization that are more suitable for developing your business, let's say. So non-profit organizations are not good for that. On the other hand, I think that OpenAI was initially a non-profit organization as well. So
Yeah, they were, they were, but it's in the name, right?
yes, yeah.
But
So so
then,
I so so I- so in case of non-profit organizations, as far as I know, it's also legally allowed to have something like business operations as well, but that's not something that we do here.
all right, thank you. It
Okay.
answers my question. I'm
Okay,
sorry if
good.
it was a more general question rather than a.
That's fine. Thanks. All right. Do
Thank you.
we do, do we have any more questions regarding the organization and so on, or everything is clear? Maybe I'll go back to the slides about the workshop before we proceed. There are some questions on the chat, so let me just check them for the last time before I give the Zoom. There's a question about the certificate. Um, yeah. So. Regarding the certificates, as we said, there will be there will be a quiz released probably tomorrow, and we'll just give more details later, right? Because as I said, this is the first time we organize this workshop, so we want to wait to just ensure that all the questions from the final tests are covered during the workshop, right? And then we'll release it. Regarding the recording, yes, we are recording the workshop now, and we are going to record it tomorrow as well, and we hope to publish the recording on our YouTube channel. Regarding the Q University program, so let me go back to this. So it's a program of Qword actually. So as I told you, in Qword we collaborate globally to develop educational materials. We already have something like a Q course or Q class, which is something like a quantum computing semester. So we already have materials for one or actually even two semesters for quantum computing studies. But of course, we work on other materials, and we would like to. So at the end, we would like to have curriculum for the whole quantum studies, a few year-long quantum studies, like undergraduate or graduate studies in quantum technologies. So it's still in progress, but as I said, we already have materials for at least two semesters for quantum studies. And based on this material, some universities have already started offering some courses, like the University of Latvia, for example, from Riga. I also heard that there have already been some classes in Poland at the University of Warsaw based on the materials developed by QWord as well. So some universities are already taking advantage of these educational materials that are also available for free. All of them are open source. and you can find the links to repositories on Keyword website. All right, do we have more questions? Let me check the chat once again. Yes, these materials are freely available. The question, what do you think is the level of workshop in the quantum? So I would say that it's something bit, so it's we require some quantum knowledge uh, already, but not very advanced, I would say. So it's something like an intermediate level workshop. Okay, I think we need to start the merit session because we have some very general questions now, so not directly related to the workshop. You can ask your questions later on on our Discord. So let me stop sharing my slides now. And Jacob, if you are ready, you can start sharing your slides. Okay, so Jacob, the Zoom is yours. We can start. I think you are muted now.
I needed to recover my screen.
Oh, okay. All right.
Yeah. So you can hear me now?
Yes.
Yep.
I can hear
Excellent.
you
Well, this is the first session. Welcome to Quantum Machine Learning Introduction. I'm Jacob Cebulski from Enquantum, Melbourne, Australia. It's evening here and it's warm, even though it's autumn. Okay, we don't have a lot of time, so I'll be trying to be quick. I'm going to talk about the aims of this workshop, then introduce you to parameterized circuits, data encoding, measurement, model training, optimization, and other things. So it's going to be tough for some, but easy for others. That's our core team. Myself, at the bottom left, Pavel Gora, coordinator of QPoland and CEO of Fundacja Quantum AI, who just talked to you. Sebastian Zając, assistant professor of SGH Warsaw School of Economics, and Tomek Rybotycki, QML researcher associated with a number of organizations. We also have mentors. You're going to meet them on Discord. I'm not going to talk a lot about what is quantum machine learning because I imagine you joined this workshop because you already know something. Basically, it's an intersection of machine learning, classical machine learning with quantum computing and some mathematical foundations borrowed from quantum mechanics. There's lots of published applications of this technology. Some to help people in medical and well-being biotechnology area, some to solve problems in the environmental problems, some economic, some societal. I'm not going to get too much into high-level things because I imagine you joined this workshop because you want to get some understanding and practical skills in developing quantum machine learning models. So the general topics could be gained at some other seminars. We have here people who come from quantum computing area and people who come from machine learning area. And I imagine that the aims for the two groups will be slightly different. Some will want to learn about machine learning for QML, and some will want to learn about quantum stuff in QML. I'll try to address the middle ground. So there'll be always something new for everybody and something extremely boring for everybody. So keep it in mind. We have people from two different sides of the spectrum. We're going to talk about parameterized quantum circuits. In other terms, variational quantum models and variational quantum algorithms. What are they? If you studied quantum computing, you met with quantum circuits. They are circuits of qubits, operations on those qubits. Some operations are single qubits, or multiple qubit operations, especially the entanglement or CNOT operations, and there will be some measurements. The thing is that the quantum computing circuit is rigid and is fixed. It was submitted to quantum machine for execution, you get some results, but you can't really alter it. If you want to change the input data for it, you need to create a new circuit. So how can we parameterize them? So basically we create some templates for the circuits. It's an abstract template, which normally the parameters are attached to operations. And to be able to execute parameterized circuit, you need to instantiate them with specific values, create the physical circuit, and submit for execution. So that's the process. The structure of the circuit is quite varied, but each circuit would have some feature map which accepts parameters for encoding input on the left-hand side. Some will be the ansatz, and the ansatz will consist of multi-layers of parameters and entanglements. They're usually called the rotational blocks and entangling blocks. And there would be the measurement block at the end. Now, this is the theory because it's not necessarily in that order. So it's quite possible that the input block could be repeating across the circuit. And that's what's called data re-uploading. And that's a quite popular method, especially that it improves optimization techniques. So that's the structure of parameterized quantum circuits. And this structure will be subjected to training and optimization. Now, how do we encode data in the circuit? So if you've done some quantum computing, you already know that you could make data appear in the circuit in a variety of different ways. So we know data encoding techniques such as the basis encoding, angle encoding, amplitude encoding, QRAM encoding, and many, many others. In this workshop, we're going to look specifically at angle encoding throughout because it's the easiest, and it gives you the possibility of encoding floating point numbers, and this is encoded as state rotation of individual qubit. And the rotation is we performed with standard quantum operations or gates, such as Rx, Ry, Rz, of phase rotation, or even operation which include all rotations in all possible directions, x, y, z. So how the rotation happens, it usually starts with some specific qubit state. It could be 0, but it could be the Ket state, the Hadamard state in the middle. And if it starts at the 0 vector, the rotation would be to the right, perhaps. And you could rotate it all the way around the Bloch sphere. If the rotation starts with the Ket state, you could rotate up, let's say, to encode negative numbers, or right to encode positive numbers. And so that rotation will be reflected in measurement later on. If you measure directly what you rotated, the measurement would give you the amplitude of the qubit state, the vector state. And the amplitude of rotation to the right or rotation to the left would be indistinguishable. So if you have a vector turn left instead of right, and you measure the amplitude, will be identical amplitude in both cases. So that's a bit of ambiguous there. So that's the angle encoding, and you'll see that in action many times, and you'll see what are the problems with angle encoding in just a minute or a second. So angle encoding, the good, the bad, and the ugly. It's usually the ugly. Imagine that we have a function with domain of -6 to 6, the range of angles that you want to encode. It doesn't matter what is the y value of the function. So you want to encode directly that range of values from -6 to 6. So you could imagine it's almost from -2 pi to +2 pi. So let's look what happens if we start encoding from to the right, from the positive values. So we encode first all the values from 0 to pi fourth, then pi. Then we continue encoding. We can show it as purple arrows. We encode further. We go up to this point, up to value 6. If we now encode the negative values, the orange arrows, we encode down to the left and so on. What's the problem with this is that now we can see that if you pick any rotation on that block sphere, there's 4 possible values which are going to map into any specific amplitude. That will create havoc with the model and the model training. It's ambiguous encoding, and it will show in very poor optimization of the model. So we need to avoid that. So we violated principle number 1. Distinct values should be mapped onto distinct amplitudes on measurement. So keep it in mind, and that relates to angular codes. Let's look at the solution on the right-hand side. The possible values encoded in from 0 to pi. That's pretty good because every single vector in the space will have the unique amplitude, some positive, some negative. Well, that's great, except that in some cases, let's say function sine, the function sine oscillates up and down, which means that there will be identical values in function sine that will be encoded in 2 different spots in that range of 0 to pi. And that means that there will be 2 amplitudes corresponding to a single value. Well, that violates the second principle. The same data values should always map into identical amplitudes. Otherwise, you're going to have problems with training. So this is the starting point. Rubbish in, rubbish out. That's known from any computing, classical or quantum. You need to put a lot of thought into how you encode the data that you're going to present to the model during training. On the other side of the spectrum, we have measurements. So the question is, what can we get from the circuit once it does all the work, it's trained, and then we want to measure the result? So the measurement is simple. You could measure 1 qubit, multiple qubits, all qubits. You could measure them in groups. But what does it mean? So measurement is one thing. The outcome of measurement is another thing. But what's important is how we interpret the results. And so that's actually is not given a lot of thought in literature, but let's look at it now. Can we get a logical value out of measurement? If we measure a single qubit, that's on the right-hand side, if you measure it repetitively, then you're going to have some kind of a frequency chart. There'll be one high bar and one low bar. And the higher frequency could be interpreted as the value of the result. Okay, so 0 on the left-hand side will give you perhaps false, and the short one, 1, unfortunately, will not play. Can we get integer? If we get the probability distribution, so we measure probabilities, then we could look at the highest probable outcome, which is this bar here, and we could look at the bit representation of that outcome, the qubit results, to be an integer that's returned from the measurement. Or we could perhaps return the height of the bar as a floating point number. So that's we have here flexibility. What if we want to return a floating point number, which is not the highest bar? Perhaps we could always look at the height of the bar, which is 0, 0, 0. It's easiest to find. It's always the beginning of the list. And the height of the bar would be the floating point representing the result. So we can represent logical values, integer values, floating point values, and we could even return the entire probability distribution as the result. And there's quite a lot of applications which want to have a distribution as the result. You could train the distribution as well. So, yep, we could encode almost anything. We could decode almost anything. Now, what's important is what's in the middle, the ansatz, which is the parameterized section of the circuit. So ansatz design is the same picture you've seen a moment ago. We have the feature map on the left. We have ansatz in the middle. The ansatz consists of layers. Each layer would have a rotation block, entangling block, and then we have measurement. The feature maps could vary in structure and function. Here I show you the simplest because we used angle encoding. But we could have actually a complex structure, a complex circuit here, which could be trained independently of the ansatz. And that's what people do quite often. They have good results. The ansatz itself could vary, could have different width, the number of qubits, different depth, the number of layers, different dimensions in terms of number of parameters, different structure, his flat structure, but you could have funneling out, funneling in, and you could have to stitch that ansatz by hand rather than using one of the Pendelane or Qiskit library functions. And you could have different entangling blocks. Pendelane by default gives you very simple entangling block, but if you're familiar with Qiskit, you could have about 6 or 7 varieties of different entangling blocks before you go and customize it yourself. Pendelane seems to be the tool that you spend time with and you play with it a lot. So ansatz layers definitely consist of rotation operators and CNOT games. In terms of optimizing it, we would need some cost function, and a lot of standard cost functions available, like R squared, mean absolute error, mean square error, and many others, including cost functions like Kullback-Leibniz divergence, which is good for distributions, and different optimizers. And most of the optimizers which live within Pendelane, they are gradient-based optimizers, such as ADAM or Nesterov Momentum Optimizer or SPSA. Linear approximation methods like Cobila or nonlinear approximation methods, BFGS. BFGS is actually built into Pendelane, but Cobila is not. You would have to interface to some other software like PyTorch to gain access to that. And we have also quantum specific optimizers like quantum native gradient optimizer, which could be defined even as a circuit. So it's great. The circuits could be executed on simulators like CPU that you probably do, accelerators, GPU, and real quantum machines on QPU. So we have a richness of the environment. Now, I did mention it, I should have mentioned, but here the red that when we talk about measurements, think about it, that if you add one measurement, you double the number of outcomes. So if you have n measurements, if you measure all qubits, that will give 2 to the power of n outcomes. So when you have the new machines coming out, everybody's crying out to have more qubits. This is actually a problem because you need to be smarter about how you measure the outcomes. You need to start cluster qubits into groups. You need to interpret the measurements in specific ways. It's a nightmare, but you have more qubits. Now, when we increase the number of qubits in a simple ansatz, you need to think that every qubit you add, you increase number of parameters, you increase number of entanglements across all layers. So that increases complexity as well. Also, the number of states represented by the circuit grows exponentially with the number of qubits. So at some point, this whole structure goes into Hilbert space, and this is where you solve the problem in high-dimensional space. So you keep it in mind that complexity grows with the number of qubits. Now, before we get into optimization, let's start with classical deep learning models. The classical deep learning model, it will have layers of weights and biases, and those weights, each weight is a dimension in space. If you vary individual weight, you vary the value on that axis in a multidimensional space. So if you look at a specific model, if you look at all combination of weights and biases in the multi-dimensional space, if you have, say, 200 weights and biases, we talk about 200-dimensional space. And each of those dimensions, you could vary the values attached to those parameters. And together, the combination gives you a model. And the model is a dot in a multidimensional space. And in 3 dimensions, you have 2 parameters, θ1, θ2. And the elevation is the actual error between the result the model produced and expected value to appear is actually the cost across all training data you have to your disposal for the calculation. So all the dots here represent different models with different combination of parameter values, and the height of the line is actually the cost value. Together we have a cost landscape. The cost landscape has got bumps, valleys, and hills. And this is where Optimizer is looking for the minimum cost, the best possible outcome for the optimization. And to do that, it needs some gradients on this landscape. And the gradient is follows down. So the arrows down are the gradients attached to the surface of this multidimensional space. You're looking for the spot with zero gradient, and there could be a lot of little spots like this on the way, which are local minima, and use techniques like the first or second momentum to jump out of those local minima, or some stochastic interference on the way down. You could hop out of the little pots and holes to reach the global minimum. That's what happens in the classical models. And we use backpropagation because in backpropagation, a classical model, not only you could go down the hill on this landscape of multiple models, but within a single model, you could very efficiently change the parameter values so that you could go down in a very efficient way. The gradients in this classical model are local. That means the changes to individual parameter value changes the gradient only locally in the vicinity of that particular parameter value. Now, what happens in the quantum space? In the quantum space, it's getting more difficult because we start with some kind of a mathematical model representing the problem. Let's imagine we have a problem in physics, and we try to minimize the global energy of some system, and Hamiltonian would represent all possible elements of the energy. Okay, Ismail, you have to switch off your microphone. The Hamiltonian defines some geometry in Hilbert space with the optimal solution associated with the optimum energy, usually the Grant state, the Grant energy of that system. That's what we have here mathematically. It's shown here as a pink area, with the real solution being the pink dot at the bottom. The problem is that Hamiltonians don't map directly onto the ansatz of a quantum circuitry. So the quantum circuit only approximates the Hamiltonian, and therefore the problem. So we have the blue space, and it has some global minimum, which is different from the real solution to the problem. And if we look now at the cost landscape, which depends on the optimizer, the cost function, and possibly the data available for training, that landscape is actually aligned. It's a lower dimensional space within the ansatz space. So what you find here as a minimum is only a local minimum to that landscape, which is not even the global minimum of the ansatz, is definitely far away from the real solution. So we have a problem here with different abstractions of the problem. So we're trying to do the best, and we try to represent the problem as closely as possible to the reality. If you work in physics and chemistry, you could really find a good representation of the reality in your quantum model. If you work in something like logistics or finance, you are struggling. Okay, so warning, you will never get things perfect. Now, but that's not the end of it. The optimization of quantum model needs some unique approaches because we have something called non-local gradients. What does it mean? Here we have an example. We have two qubits, one qubit and another one with two different parameters. So we have θ1, θ2, and imagine those qubits are entangled. So if you try to, in optimization, try to manipulate one parameter on qubit 1, then you'll find that the parameter in qubit 2 gets changed as well. So not only the parameter values get changed, but also the gradients attached to those parameters get changed as well. So that's actually a problem. We have those non-local effects in the optimization of quantum models, which do not exist with neural networks. So there are special techniques for that. So we have this quantum native gradient and quantum native optimization, which are aware of those issues, but they're not as efficient as classical optimizers. So we still use classical optimizers. We also can't use backpropagation. Backpropagation requires access to the state of the model, which we cannot directly access. We have to measure the state of the model, which collapses the state. And from collapsed state, you can't go back. So we have no ability to backpropagate efficiently, but there are some techniques which imitate backpropagation. Gradient descent is still available, but gradient descent usually utilizes global gradients, which means the gradient on the global space of multiple models in the landscape of all models. We have other non-gradient techniques, stochastic optimization techniques. We have particle swarm optimizers, so we could try them on quantum models as well. That takes us to PenDeLane. In a minute, I'll give you a demonstration. We are a bit late because my session started late a bit. PenDeLane and Qiskit are probably two most prominent software development kits for quantum machine learning. And PenDeLane was created specifically for quantum machine learning. So PenDeLane, Xanadu is advertising PenDeLane as a QML product. First of all, PenDeLane supports differentiable programming paradigm. So what it means is that PenDeLane treats everything as a function, and it's a differentiable function, which can you could propagate gradients through that function. Okay, so that's different from Qiskit, where the circuit is a separate object. Here, the circuit is a side effect of function execution. It integrates seamlessly with Python. It has a range of operations, same like Qiskit, state preparation, gates, measurements, supports flexible quantum algorithms. It's not as rich as Qiskit, does not have such huge library, but it's stable, unlike Qiskit. It executes on simulators, on accelerators like GPUs, on variety of quantum hardware. Xanadu is a company producing photonic machines. And so you have another layer, another software called Strawberry Fields. PenDeLane and Strawberry Fields are two songs from the Beatles. Someone must be obsessed by the Beatles there. So Strawberry Fields is actually a layer of software over Xanadu machines, which gives you direct access to photonic gates and so on. We have ability to mitigate errors and simulate errors. And we have a variety of different gradients packages. And some of them you could interface directly from foreign packages like JAX, PyTorch, Keras, TensorFlow, NumPy. And we have interfaces to the optimizers and the whole richness of those packages. We're going to show you how to interface with PyTorch. And it's excellent for hybrid quantum classical models. What it means, you could mix and match classical functions with quantum functions as long as they're all differentiable functions, and you could pass gradients between them. They interface well in a very flexible way. So you could link, you have matrices, you have classical programs, and you could have quantum functions and quantum circuits. They could be all interfaced together and working together. So it's a great environment, especially for researchers. And you have also hardware-specific gradients and high-order derivatives and a variety of quantum models, but most of the models we stitch by hand because we don't have such a huge community as it is in Qiskit. So I'm going to show you a demo. A demo will create a simple PenDeLane model to fit a very simple function. You're going to learn how to initialize the model weights. We're going to look at the structure of ansatz, the performance of it, create the minimalistic quantum model and see that it actually works. Learn how to interact, what's the interaction between data encoding and ansatz, and look at different entangling, and then go into data number 2, and you're going to sit and cry. And that will be homework, to go and cry. Okay, so let's do this. I'm going to stop this presentation. If you have any, there's actually some books I recommend, like Dancing with Qubits by Robert Sutter. This second edition. It's a great starting point for the mathematics in quantum computing, not necessarily quantum machine learning. It's a fantastic book by Maria Schulde and Francesco Petruccioni, Machine Learning with Quantum Computers, second edition. And it's a really nice book, a practical guide to quantum machine learning and quantum optimization. They're all there. There's a couple of papers which I throw in as well, which give you an overview of PennyLane. It's an older paper, 2020, but it gives you some overview of what you can do with PennyLane and a variety of different quantum machine learning models applicable with applications to science. Okay, if you have any questions, please put them on Discord and I'll be answering them later on. But we are on the critical line. And so let's get into demo. First of all, I think I enlarged it a bit so that you can see the letters clearly. There's two notebooks there, which you can study at home at your own pace. Explore measurement tests and explore tiny model. The first one gives you ideas how you encode and what you see when you measure what you encoded. And there's a different type of measurements that PennyLane supports. So some expectation values measurements, probability values, state measurements. So there's a lot of measurement types, and PennyLane is fantastic with measurements. It has about 6 or 7 different measurements, which in Qiskit you would have to do by hand. You would have to actually untangle the results from the measurement to see what you got. So that's one. It's got here some charts and shows you this is what you encode and this is what you get. I'm not going to cover that. Another one is to explain QML principles, especially when it comes to gradients. So you can actually see what gradients do. The gradients attach to individual variables, to individual values, and they propagate through the tensors. And so very simple first circuit here. But we're going to dive straight into what you're going to work with, which is a simple QM model in PennyLane. And we're going to try to fit a sine function. It's a standard task people show everywhere. And then when someone is trying to do it and changes one parameter in the sine function, nothing works. And people say, why doesn't it work? People say, you need to make your model richer, and nothing works. It doesn't work because of that. It doesn't work because you're going to find out why it doesn't work. You're going to try to resolve it, and you may want to go back to my presentation to figure it out. So let me just restart the kernel and walk you through this. So that's actually, in GNOME, the first cell, it just tells us that the table here should be aligned to the left. This table explains in every notebook. It shows you what data you're going to use, 2 sets of data, sine and a more difficult sine, 40 minutes. Today, because we start a bit late, so this demo in my presentation will cut a bit of your break, but hopefully you have at least half an hour break. And you have to perform tasks. In session 1, this notebook is annotated and say, here you answer task 1. In session 2, I'm going to say, yeah, more or less here, this is where you do task 1. And session 3 tomorrow, this is like, you find out where you need to find what you need to modify. Okay, so we guide your hands today, but not tomorrow. So the first task is to just listen to what I'm saying. And then you have challenges. And usually the challenge asks complete unfinished tasks. And the tasks, all of these, the contents will be in a quiz. And then you have some more difficult tasks. Okay, so what we're going to do, the first of all is we're going to load PennyLane. And the first thing to note, apart from the fact that PennyLane wants always to say PennyLane available as QML because the that promote the product as a QML product. Great. The second line is actually more important. It says, Pendelane redefines NumPy. What it means is that if you create a NumPy array, it becomes a tensor straight away. And apart from that, every function in NumPy is available in Pendelane version of NumPy, and they keep them updated. So keep in mind, we're not using true NumPy, we're using NumPy, which works on tensors all the way. You can see here, task 3. We have settings here. How many samples I'm going to generate. So the sign will be based on 64 dots. We're going to here define number of qubits that we're going to create. They're called wires in Pendelane. Number of layers in the ansatz. The number of epochs for training. We start for 20. If you go to the next notebook, I'll start with 50, which is my preferred. And if you have a very slow laptop, I suggest you keep it at 20. And if you have, like me, you sit on a large gaming machines, which I use specifically for quantum stuff and not gaming, I don't play games. Remember that. And then we have seed, so that your results will be like mine. So we start with 2 qubits, 4 layers. You'll see that model in a minute. Some data preparation, and this is where hairy stuff starts, because I said data preparation needs thinking. This is where problems start. You make it bad, you don't get good result. Okay, so we have here a sine function in a domain from -6 to 6. We change the shape so that it's a set of sub lists, and the function sine, which generates a model. I'm going to use the model, the plot. Okay, so this is what the data looks like. And by the way, if you get something like this, what I get, ever, there's a trick to it. You just move it to the right and then the contents appears. Okay, something wrong with the amount of memory for rendering the output. Okay, so here we have the next bit. We specify what device this program is going to run on, and I use something called default qubit. There's something called Lightning Qubit. The Lightning Qubit is a faster simulator of Pendelane. There's also something called Lightning GPU. It's a simulator running on GPU. You have also other simulators like there's a default mixing and so on. So there's many more, which means that you could use a variety of different devices to run Pendelane programs on. Let's stick to default qubit to start with. At the device specification, you could do other things. You could specify what differential methods you want to use, whether it's adjoint, which is good for matrices and good for circuits, and parameter shift, which is a great way of calculating gradients for quantum systems. Then we have a simplistic model. Here's the first model. The first thing you're going to see in this session is that the quantum model is a function, and the quantum model is prefixed by a decorator, which says it's a Q node. The Q node is actually a circuit. So you basically say here with the decorator is that this model is going to run on the device I just created, and I'm going to use differential methods called adjoint. It's basically a differential method which is based on matrix and its inverse matrix. That's because the circuits are reversible. And what's going to happen is that this function is called QNN model 1, and the circuit will be called the same way. So actually that function will be called something different a little bit. It will be called underline QNN model 1, and the circuit will be the Q node, a quantum node, which is executable on this device using this differential method. And what the circuit does, when the function runs, as a side effect, it will create a circuit. So it calls QML, which is Pendelane. It says, first, attached rotation in around y axis by that amount, which is passed by argument x, and put it on y as 0, which is qubit number 0. And then after that, put a block of basic entangled layers. You're going to see them in a second, which is initiated with those parameters. So the model takes parameters to initialize and could also have some input data, which could be attached to rotations. And we specify how many wires we're going to have and what type of rotation we're going to use, whether it's Rx or Ry and so on. And we're going to measure expectation value, which is in the direction of z-axis attached to qubit 0. Make sense so far? I hope. So let's define it. We defined not only the function, but also the circuit. Then I have two other models of similar type, which you're going to investigate on your own. And here I'm saying you could attach any of those models to a variable QNN model. So just change 1 to 2 or 3 to be able to access it. Okay, so we created a model. Let's look at it, what it looks like in a second. Here's also I create the cost function, which is mean square error cost function, and the function which can be run on the model using specific parameters. So here we have vectors of targets and predictions. And here we have the cost function, the same cost function, but applied to model initialized with some parameters on given inputs to give targets. Okay, so this is actually the real cost, the second one. Let's look at the model. Okay, here is what we have. We have something called basic entanglement layers, which is like a neural network, is layer by layer of weights. And it means it's got some shape. And the shape usually is the number of layers. Each layer has a number of qubits. Each qubit has a number of parameters. Okay, so you could either do it by hand or you could use some helper functions. Like in here, we have basic entangled layers shape. We specify how many layers we use, how many qubits. And it's also something called strongly entangling layer, which you'll see later. It shows you what the shape looks like. It's very important to match shape for initialization values with the shape of the circuit. And this is just a test. I'm going to create the whole lot of numbers in the specific shape. Whoops, I didn't want to do this. Okay. And get the first value from the X with the data vector and apply the model to weights and the values. We don't need to submit it anywhere. It will be submitted automatically, unlike what happens with Qiskit. So we submitted the model which is initialized with specific values. So the parameterized circuit turns into a physical circuit. The input data is actually encoded and it's executed, and we got the result. Okay. Now it's actually happening on some random parameters. So if you want to make a good fit with the data, we need to train it. Now this is actually how we could produce the visualization of it. Note that visualization is specific for given parameters and given input. And that's because the circuits get created as the function runs. That's what happens with photonic machines. Photonic machines have a laser. The laser creates some kind of interference, and the interference is propagating into the future, into the space. It doesn't exist as soon as it's created. Like the function runs, it's run, it's gone. Okay, so that's what happens here. If you want to see Qiskit-like presentation, that's another way of doing it. You will use different draw method. So the draw method is a function taking a lot of arguments, but that returns the function to draw, which is specific for that model, the parameters and the inputs. Okay, now we are going to train it. We're going to select an optimizer, Adam optimizer you should be familiar with. We create the parameters of a specific shape. And then we get into training loop, which is exactly like any other training loop, which means we're going to create a list to collect costs. We're going to iterate it through to a number of epochs. Here is 20. We're going to optimize a step forward and backwards, calculate the cost. The cost is returned, and the new version, better parameters, is returned. We save the costs, and we iterate further. We print something on output. Let's see how it works. Because it's very fast, because a very simple function. So execute it in 5 seconds. Maybe on your small, tiny, mini laptop, it will be 20 seconds. So we improved it from 0.6, the cost, to 0.001. And let's look at the results. I collected all the data in the history of costs. So this is the result. It doesn't look pretty. Maybe if we extend it into more epochs, it will smooth itself out. Maybe we need to do something about the model to get it better. Let's see the fit. So what happens is I got the model. I will, for each different value of X domain, I'm going to run the model on the last parameters. I could find the best, but the last here was the best. And get the predictions, and then plot the predictions against the actuals. It's almost right. You could get better. You could have a suspicion that it echoes the value, so it's not actually doing anything, but we can investigate it. Okay, so that's the end of the demo. We are a bit late, I imagine. Let's go, and you're going to run it on your own. Let's try to go through task 1. We've done it. Task 2, which is change the range of initialization values and see the impact of your changes on the actual execution of the model and the result. Okay, clear for everybody? We have 1 thumbs up. Woo! So it's clear for 1 person after 100, out of 100. Oh, 2. Great. Okay. Now, what's going to happen is that those of you for whom it is totally clear what to do, go ahead and do it. Those of you who are still confused, I'm going to step you 1 item at a time. Okay. So if you're lost a little bit, I'm going to walk you through the steps of those tasks, and I'm going to demonstrate them now. But if you are confident, go for it. When you finish, go for the challenges. Okay. So we're going to switch now to, most of you, to the Discord. If you have any issues and questions, put the questions on Discord. Here I can stay with people who want to see more of me. I'm going to here demonstrate how to solve those tasks one after another, very, very slowly until good. How is timing, Pavel?
I think it's not bad. Let me check the agenda now. All right.
Sorry?
Okay.
Okay.
Okay. I will check the agenda now. All right. Can you hear me well, by the
Yep.
way? Okay, good. Okay. Demo.
We're 20 minutes over.
Yes, I think we are slightly over, but
Yeah. So I
yeah,
was about
anyway,
15 minutes,
it's
15
yeah,
minutes late starting. Okay, so
okay.
but
We can do a
we have
shorter.
1 hour a break, so we could take some.
Yes. Yeah, we can shorten the coffee break.
Okay. All right. So what I'm going to do, I'm going to talk more. I'm going to look at task number 2. The task number 2 is very simple. It says, can the model performance be improved by trivial changes, such as alter the range of model initialization value, reduce high for training? So let's look at that task 2. Task 2 is somewhere here. Task 8. Have I missed it? Task 2.
Model training.
Cell 15. Okay. So here we are initializing values, initialize parameters. The high value is pi. So we initialize the parameters from 0 to pi. Normally, the advice is to initialize quantum models with small values. So let's put here a small value, 0, 1, perhaps. I'm going to now get kernel restart and run all cells, and we're going to see what's the results. Remember, I'm here on 20 epochs or 20 iterations. So let's see here. Did it have any impact? Well, in my case, it didn't, but it gets close. So, but in many cases, it's a very significant impact by reducing the size of initialization values. So the first test, it could be that if we started with a larger number of iterations, we would see the difference. So let's actually, I'm going to increase it to 50. I'm saying 50 is preferred. And I'm going to run it all. And it's quite likely that if we started with 50, we would actually see the improvement. So we actually get here very significant cost reduction. So definitely more epochs and smaller weights improve the outcome. So we actually have an improvement of the model training. And we can see here that plot of the cost, it flattens at the end, probably is not going to improve much more. And you can see now that the fit of my predictions is really spot on. It aligns well with the actual values of the function. So the first task, and we've done a good job. Everybody said it? If you find that if you're on the laptop and 50 iterations was making it very slow, it's better if you stay with 20. So in my case, it took 14 seconds. If you all takes 2 minutes, you're in trouble. You have 13 seconds. Hey, the Mac works perfectly with 50. Okay, so we have here some, if you get something over the minute, let me know here. 17 seconds, that's pretty good. It's a real test of can you actually do quantum machine learning on, on your machine. Okay, that's pretty good. But believe me, with the next session, we're going to take a long time to train the models. Okay, so that was task number 2, 19 seconds. Task number 3, can you improve the quantum model by changing the ansatz size? Using more qubits or less qubits, more layers or less layers. I imagine that if you work on a small machine, you want to reduce. So I have 3 layers rather than 5. Okay, so I'm going to try it. I'm going to increase number of qubits to 5. Note that at the bottom of this here, I say, write your observations here. It's just for you. But if you got a good result, you're going to pick it up and write it down. So my cost is actually that much. And you may want to stick it in here. Was a task 2. So that we could see, are we improving or not? So I'm going to increase number of qubits to 5. But you may want to Oh, not 5, 4. Make it 4. You may want to make it 3 so that you don't kill your machine. Normally, I would suggest change one thing at a time. So rather than saying more qubits and more layers, just see number of qubits, the effect of that. So restart and run. And see what we have. So you can see now we have 4-qubit circuit. That's good. And we train it. Okay. Okay, the cost wasn't as small as possible, but it's possible that with the increased size of the circuit, we need much more time to train it. So I wouldn't discard it as a bad test. I mean, look, we hear that the cost is 0.000 something. That's a low cost. I'm going to record it anyway. It's my task with 4 qubits. You can see here was 2.7 to the power of 10 to the power of minus 5. Yeah, it's close. Here we had 2 qubits. 4 layers. 4 qubits and 4 layers. So I suggest always record your results so that you know what's the outcome. Anybody got anything with layers? Well, someone got 0.00156. Okay. So even though we have we set the seed the same way, it looks like there's some variation still applying there. I don't know where from. If you start from scratch, that means you say restart the kernel, run all. We should be all getting very similar results. Okay, we could play with these. Let me just change back to 2 qubits as it was and increase number of layers. I suggested 6. Oops, that was supposed to be 2. In the next session, I'm going to talk about how to do it properly because nobody is going to sit and play like this. Just let's try 2, let's try 6, let's 4, and record it by hand. We should automate it and send it as a bad job and come the next morning and pick it up so that you could have live. So I'll talk about that in the next session or the one after, can't remember. Okay, so here we have the result. So it looks like increasing number of layers does not have such an impact as increasing number of qubits. But the thing is, it's all dependent on data. So here we just kept oops. We had here 2 qubits and 6 layers epochs. So I'll make it shorter. It's almost the same result. So I would not say which is better, which is worse. Okay, so we are playing in the dark. I think that those changes seem to be quite irrelevant because the model is performing so well. We are overtraining the model. That's my feeling. We're overtraining the model. It's great when it comes to training performance, but may not be so good on testing. I don't know how we test it. Okay, so Everybody got with some tests? Okay, so everybody gets very similar. Mathematical Hilbert, okay, of dimension 6 versus 2. Yeah, so the number of wires will be 6. Mathematical Hilbert space is 6 versus 2. Yeah. Okay, the next test is going to be very interesting. Can the model work with a single qubit and a single layer? Here we are. Now, you would think the more qubits, you have more expressivity, more the richer environment, the richer model should catch more nuances. What if we have a 1 qubit, 1 layer system? That seems like a stupid idea. But let's say 1 qubit, 1 layer, and run this. Intuition says it's a waste of time. Maybe we'll get an error. There is a method called single qubit encoding. Yeah. Let's see if the single qubit works here. Well, yep, very quick. It actually gives us the best cost. This is weird. Should not be happening, right? It's very smooth. What? Tomek. It's a method, I imagine. Okay. Let's record this. So my system is running out of memory. I need to wait. My system says, enjoy looking at it. That's 1 qubit, 1 layer. And we have the best outcome so far. Can anyone explain this? Variation quantum eigensolver for task 4. Let's see task 4. You could do anything you want.
Can I give explanation?
Sorry?
Can I give explanation for better result with 1 qubit?
Yep, tell us.
I think 1 qubit means we are dealing in 2 dimension, 2D, and 2 qubits means we are dealing in 4D. So our sine wave is in 2D only, and hence it is best approximated with 1 qubit. Am I right?
Probably not. I mean, it's partially right, but there's something more obvious. Okay, because our data has 2 dimensions and predict why. Okay. Here's a hint. Think what a rotation of a qubit state is doing. If we have just 1 qubit and 1 rotation, and we rotate it in increments, and we measure at the end, what are we going to measure at the end? Yeah, we get sine function. Okay, so what happens here is this problem is cheating. Okay, the amplitude is cosine, yeah? But you could actually adjust that. It will get shifted in the layer, okay? So we start with a different value. So we could actually get a perfect alignment if we do nothing. It's a single rotation on a single qubit, which means that the problem here is a cheated problem. Okay, let's see what happens if we change encoding gate from Ry to Rx on that single qubit system you have. Where are we doing it? Here, the model Y, we have Ry. Let's change it to X. What do you think is going to happen? Someone says there'll be no change, same as before. Okay, let's see. And tell me why. The system learned nothing. Any idea? Let's look at a circuit. Oh. Yeah. So here we have rotation around x-axis, and we are training the model around y-axis. They don't intersect. So it doesn't matter how much training you do on this, it will not influence the outcome. Okay, so there's some kind of a still effect of Ry, but it doesn't actually take the value of X. So what's the solution to that? What I actually suggested here, let's keep the x-axis rather than changing rotation around x-axis for the ansatz. Let's actually change completely the way we're going to change the entangling block. Instead of using a single parameter, use 3 parameters. So we're going to change here in a number of places. In the model definition, we're going to change from basic entanglement to strong entanglement. The strong entanglement is basically entanglement around X, Y, and Z. Sorry, it's a rotation around X, Y, and Z axis. Entanglement is the same. Rotation-wise, to be similar. Okay. But let's change the entanglements strongly entangled. We're not touching model 2 or 3. We have the same cost function. Here we need to do the change because this is the initialization for a shape which was specific for the basic entangling. And now we need to have a shape for strongly entangled layers. If you don't change it, it will tell you that you got an error. So that worked. We can see the model. We can draw the model, no problems. Have a look that we now have 3 parameters, RZ, Y, and Z again. That's because you could get the X rotation by combination of the other 2. And here we need to, again, change initialization. And if you don't, you'll know because the error will pop out. And let's train it. And now it looks like we get some result. And we have a good cost and good outcome. So why did it work now? Git link for this notebook. It is in here. Hang on, I can't see it. Oh, someone posted it already. So what happened now is that because now we have rotations in 3 directions, we can actually get the good result. Okay, so we are getting close to the end of this session. I'll show you what happens next, because what happens next is very, very difficult. I ask you to change the model to second data set. I'll comment this one out and uncomment data set 2. Oops, I didn't do this. And the model looks a bit different. Okay, it doesn't look like a sine function. And if we run that, we're going to get nowhere. This is not a super challenge. See, the model is not learning much at all. There's a saturation quite quickly, and there's no fit. So I'll leave this with you because the answer to this question is actually in my presentation. Okay, so you may want to think how to fix that. No amount of changing the ansatz and adding more training iterations is going to fix that problem. Okay, so that brings us to the end of this session. Number 1, we have a break. So we have what time it is? It's 8.
Hi, I'm sorry, but can you please go again about the problem?
Okay, the problem is we changed the data set. So we could see that on a single qubit, it all worked beautifully. And we could increase the number of qubits. And I changed the data. Where's my data set here? I commented out data set 1, so X and Y. I uncommented data set 2. And then I ran the whole worksheet as it was. So it worked before on a single qubit. And now it doesn't on a slightly changed data. It looks like the system is no longer, doesn't have learning capacity anymore, or there's some kind of interference. The learning curve plateau quite early at 0.2 something rather than 0.000 something. And there's no fit. So we could not fit the data, the training data at all with what the model learned. So,
Sir, may I speak something?
Sure.
Sir, the new data set contains 2 frequencies, and the single qubit will give the sine wave only. It will not generate anything more than that. And that's why what is generated in yellow is a sine wave again, shifted sine wave. But the data set which is used in this demonstration consists of 2 frequencies, which
Okay.
cannot be generated by single bit.
Okay, increase number of qubits, but
Yeah.
and if you believe it, increase number of qubits and number of layers and see what happens. Ravi says the answer would be in the encoding limitations and challenges. That's a possibility. A question from Prahlad. Task 8 is talking about data re-uploading. And so we have 2 functions here. So I don't know if you're listening, we have time during the break, but basically model 2, it's re-uploading data across qubits. at the beginning of the circuit. So you can see that the same value is put as a rotation into qubit 0, 1, 2, and so on. And this function, model 3, it re-uploads and interweaves the feature maps with trainable parameters. So every strongly entangled layer is interweaved with a block encoding the data across every single circuit. So the data gets re-uploaded severely in a sense. So basically the question is, would Model 2 and Model 3 be applicable here? Would they help? Would they improve the outcome? You can generate, but simply will not work out perfectly as you want it to be. Okay. Yeah, it's yes, we could reduce. We could make the weight smaller, because I think when I changed the the entangling, I did not address the issue of reducing the weights. Let's see if it works. Very quickly, we could run it. Model training. Let's change it to 0.1. And if you run it, it may or may not improve it at all. All I did was to change the weights. You can see there's a slightly angle, but it's not much difference with the past. I will try to do re-uploading, but it's let's say model 3. We'll see the circuit will look very different. Let me increase number of qubits just in case. 2, as it was before. We get slightly better training outcome. The cost reduced from 0.2 to 0.11, but it's nowhere near as good as before. So we're getting slightly better fit because now we're re-uploading the values. But it's not working. It's not as beautiful as before. Okay, we need to get to the presentation, Pavel.
Could you please repeat?
Sorry?
Could you please repeat?
Okay, should we start the next session?
No, not yet. So the plan was to start it
Okay.
to have a 25 minutes break, right? So we still
Okay.
have 13 minutes actually.
Okay, no problems. Okay.
But no, I think it's better to wait. It's better to wait.
Yeah, it's better to wait. No. No, I just get confused with time because your time and my time.
Yes.
Yeah.
Yeah, so
I look at the clock and say, oh no, I'm 17 minutes late.
you can drink another tea or coffee.
Yeah.
What time is it in Melbourne now?
Oh, it's 17 past 8.
No, 17
Not bad.
past 8. Okay.
It's like I could never make the Washington, D.C. talks because it's 4 o'clock in the morning.
Oh,
Get up at 4. You guys get up at 4 o'clock in the morning.
yeah. It's good for me and Sebastian, so that's why sometimes we are invited to be moderators.
Hmm.
Okay, there are some other questions on the chat.
Yeah.
Sir, may I clear few doubts?
What do I use? High 0.1. Okay. Normally we try to make the weights small. Normally small weights are good, not zero. Zero weight is going to have problems with gradients calculation, but small weights is usually recommended. There is actually calculation for gradients. You could I would have to find it. I was trying to find it but couldn't. So there's different ways of initializing weights for quantum systems, and especially when you guard yourself against barren plateaus, the flat cost areas. And usually it's a good idea to develop complex models layer by layer. And in some cases, you could even make initialization 0 per layer, but not for the whole circuit. So small. Whether it's 0.1 or 0.01 or whatever it is, test it. The test will tell you if you got the right weights.
Can I ask one question, sir?
Yeah, sure.
Sir, can we apply amplitude encoding here along with angle encoding?
I mean,
Is that code available?
I mean, you could amplitude encoding. You probably don't need it because we map a single value. So it's amplitude encoding is good if you want to encode multiple values at the same time. So if you were going to encode a window, let's say you have a time series and you have a window moving along the way. From the window you want to get the next value. Then you want to encode multiple values at the same time. And that's where amplitude encoding is going to help you, because you could encode multiple values. In fact, you could encode as many values as to the power of number of qubits. So it doesn't apply here. It doesn't make sense. Yeah.
Okay, sir. Sir, I have one query.
Yeah.
Can we say that single qubit leads to two-dimensional space, and 2 qubits leads to 4-dimensional space? Can we say that?
Okay, it depends what you mean by that. I mean, what happens is that the dimensionality of input or dimensionality of parameter space, because they're two different things. So the question is, what is the richness of your model? So let's say you want to encode on a single qubit 10 values from on input. That's going to be hard unless you encode them separated by a lot of parameters which learn, and they get absorbed somewhere on the way and repeat. So you could actually run models on a single qubit, but it's very inconvenient. It's much easier to do multiple qubits, where the values could be directly encoded into the structure of the circuit. So this is just to show you, yep, we could get it on a single qubit. In fact, with Sebastian Zions here, we're presenting some our work at a conference, a quantum computing conference in Melbourne. And we ran multiple models, and the single qubit model was performing best of all the models we developed. And so that was unusual because it was unexpected for the time series data. But it happened. Okay. How can one come up with an effective or new ansatz design? Okay, that's a difficult question. It depends for what. Okay, so there are some ansatz structures which, like in the neural networks, they guaranteed that they're trainable. Okay, so one issue with gradient based optimization is that you want the geometry of the model to be such that you have a smooth valleys going towards the optimum value. If you have very bumpy geometry, then there's a lot of local minima. If you have the convex or concave geometry, it'll have its problems. So some ansatz are designed to give you, to guarantee to give you optimum path towards the gradient zero. Now, it doesn't mean they're good for every problem. So if you work in quantum chemistry, you want to encode the actual observable into the observables, multiple observables into the circuit, so that the complexity is actually not in the, and also the ansatz need to reflect the problems in physics in terms of symmetry and others. So, and they have very specific ansatz for that problem. Okay, so ansatz are designed for problem areas, and they're specialized in a sense. What does it mean if you have a cost of zero? It probably means that we're running out somewhere. So when I plot here, if you look at where's the model loop, you can see that I'm every iteration I print only the cost is rounded to 6 digital places. Increase that to 10 and probably your zero will disappear. Okay. I just did not want to have huge numbers. Okay, we're going to start a session in 4 minutes. Are we recording now? No, we don't record anything yet. Oh, we are recording. Yep.
Yes, the recording is still in progress. Mm-hmm.
Okay, so
we'll start in
before the
4
next...
minutes. Mm-hmm.
Yeah, I can wait another 4 minutes. Because I thought I'll give you the solution to the problem for the second data. Has anybody solved it during a break? Does the noise have anything to do with it? Yeah, we don't have any noise in the simulator. So what happens is in this simulator, we're using the state vector simulator. In Penylane, the state vector simulator uses the theoretical answer. So it understands the structure of the circuit, and it works out what should be the distribution of results, the probabilities. But you could actually specify that you want to run the circuit a number of shots. So the moment number of shots is none. So it does the theoretical approximation of the results. If you specify, let's say, number of shots to be 1,000, the circuit will be run 1,000 times, and the result will be based on the frequency distribution of the outcomes. Yeah, so we are playing with not noisy simulators at the moment. Yep. there is a simulator, I think it's called the default mixings, and it can actually simulate noise. I think it's a noisy simulator.
All right, we'll start in 1 minute.
Yep. Oh, Ola's got very nice picture. Nice picture, but not perfect. That question actually pops up. Okay, so that question pops up on a lot of discussion boards, because the simulation of sine function and fitting the data to it, it's a standard problem, whether it's Qiskit or Pendleton. It's one of the tutorials, but nobody actually addresses that problem fully. Okay, so everybody complains they can't fit it. And the answer is not, here's the code to solve it. The answer is, go away and make your model richer. That is not solving it. Okay, we're starting the session again. I'll start it with a bit of help for you people. When you move to dataset 2, some people worked on it during the break, and all I've got pretty nice picture, much better than mine at the end. But it's still not good. So you could actually change the shape and size of the circuit, apply re-uploading, and nothing is going to work, because the problem is not with the circuit. The problem is with data encoding. If you recall my presentation, I actually said, if your domain of the function of the x value you want to encode is from -6 to 6, that means when you try to encode the value into angle encoding, it wraps several times around the Bloch sphere. So we map multiple values to the same amplitude, at least 4. So that's a problem. The problem is here we start with bad data and we can't fix it. So what we can do is to change it in a simple way. Force this domain. So after you generate x and y, let's say I divide it by 4 and see what would be the result of that. I have the same distribution, but my domain changed. Now we run it and see what we get at the end. I actually have here 2 qubits and 4 layers as it was originally. And 50 iterations. And you can see I'm getting better results now. 004, 001. It's a more difficult model to learn, more difficult data to learn by the model. So I'm getting a pretty good result, and it's a better fit. So the problem was data encoding, okay? And there's also an issue here with the symmetry of data. So what happens is, the question is, why did it work with sine function? Because if the encoding is wraps around the Bloch sphere, the same values are mapping onto the same amplitude in exactly the same spots. So we accidentally get perfect fit of encoding with the data. If we shifted the data slightly, it completely did not work. We had a lot of collisions in the mapping. If we try to map this function into the domain from 0 to pi, you would have bad result as well. And the reason for that would be that we would have the same values appearing, like the value here and there, mapping onto different amplitudes, and we would create collision in the mapping. Okay, so when I mapped it simply from, so this is actually mapped now around plus and negative half pi, more or less. We have symmetry between the negative and positive mapping onto the same values. So that reinforces the mapping of that function. So that is actually the trick here. Okay, so I thought it was an interesting challenge because it explains why nobody wants to answer this question on on discussion boards, because people have no idea what they're talking about. So think you need to be very careful how you plan encoding of the values, and that will determine the outcome and the performance and the quality of your model. What I added one line. Okay, so data set 1, I commented out. Data set 2, I uncommented. I changed some things. I went back to 2 qubits and 4 layers. So it was the original setting. It doesn't matter. And here I added one line. So after X and Y were generated, I scaled the X back to a different domain. So instead of -6 to +6, it's from -1.5 to 1.5. So that actually changed the mapping of values. Instead of wrapping the mapping around the block sphere, it simply maps it at the top layer of the block sphere. Yeah, table of content will be great. Okay, let's go to session 2. Session 2 is going to be different.